So hello everyone. Today we're going to receive Abhilash Sarwade. He received a bachelor technical degree in physical science from the Indian Institute of Space Science and Technology, IIST, in 2015. He's currently pursuing the PhD degree in physics at the Indian Institute of Technology, Guwahati, in India, as an external candidate since 2023. Since 2015, he's been working as a scientist engineer in the Space Astronomy Group, URL Satellite Center, and his research include solar physics and space science instrumentation. So welcome to CRAAM, Abhilash. The stage is yours. You have over 1 hour if you need. Please welcome to our group.
Yeah, thank you. Thank you very much. Thank you for inviting me. In this talk, I want to talk about the X-ray spectrometers on ADITYA-L1, named SoLEXS and Helios. So let me start with a brief introduction to our group, which is called Space Astronomy Group, which is part of your Satellite Center, ISRO, Indian Space Research Organization. So we have a unique capability here that we build our own space science instruments and we do the space science data analysis with them as well. So in past, we basically conceptualize the space science payloads, we develop them, we develop the hardware, we space qualify them, and we deliver it to some of the premium scientific missions of ISRO's. In past, we have delivered our payloads to ASOSAT, which was one of the India's first dedicated astronomy mission. We have developed and delivered our payload to XPOSAT, which is an X-ray polarimetry mission for astronomy. We have developed for Chandrayaan, which is basically lunar-centric missions. And of course, we have delivered our payloads to ADITYA-L1, which I'll be talking about in this particular talk. So we have basically expertise in building the X-ray, space-based X-ray payloads. And we have built different kinds of X-ray payloads for different type of applications as well. So for example, in 2015, we delivered a scanning sky monitor on board AStroSat, which is basically a gas-based X-ray detector, which has a large field of view, and it scans for the X-ray transients to point our different telescopes are there. So for Chandrayaan-2, we developed and delivered CLASS, which is basically a mapping of the lunar surface. And of course, for ADITYA-L1, we have developed two payloads, SoLEXS and Helios. And XPOSAT, we have developed XSPECT, which is X-ray spectroscopy and timing for neutron stars. And of course, in future, we are planning to develop auroral X-ray imaging spectrometer as well. So what I'll do, I'll talk specifically about these X-ray observations from SoLEXS and Helios on board ADITYA-L1. So ADITYA-L1, just to give a brief introduction of what ADITYA-L1 mission is. So ADITYA-L1 is ISRO's first dedicated observatory class mission. Aditya literally means the sun in Sanskrit, and it is currently orbiting around the Sun-Earth Lagrange point L1. So as you can see here, it was launched from Earth here. This is the Earth and this is the Lagrangian L1 point. So it was launched in September 2023, and it was inserted in this huge orbit around L1 in January 2024. Since then, at this vantage point, it has been continuously monitoring the sun at different wavelengths with different suite of instruments as well. So just let me quickly list out what are the different instruments that are present on board ADITYA-L1. So on top, I hope you can see my cursor. On top, there are two telescopes, VLC and SOOT. So VLC is nothing but visible emission line coronagraph. It's a coronagraph which is supposed to go very close to the solar disk, about 1.05 hours. And on side of it, it's SOOT, which is basically a solar ultraviolet imaging telescope. It captures the solar images, full disk solar images in a lot of UV filters. We have some of these in situ particle measurements and in situ magnetometer as well. which captures the in situ particle flux. And of course, we have Helios, which is present here inside the deck. And we have SoLEXS, which is mounted on this side panel here. So they are very small payloads as compared to these huge telescopes on top of it. So SoLEXS is Solar Low-Energy X-ray Spectrometer, and Helios is High Energy L1 Orbiting X-ray Spectrometer. And you can see schematic of these two payloads. So these are basically very small 200 cross 200 cross 200 dabbas. These are very small instruments, small, very compact instruments as compared to huge telescopes that we saw. So to go into the bit more detail into the specifications of SoLEXS and Helios. So SoLEXS observes in the energy range of about 2 to 22 keV, which is traditionally called as soft X-rays. And Helios observes in the energy range of 10 to 150 keV, which are traditionally called as hard X-rays. So to observe this energy range, SoLEXS uses two Silicon Drift Detectors or SDDs, and Helios uses two types of detectors. Two CDTs, which is used to which used to detect the energy range between 10 to 40 keV, and two CZTs, which are used to detect energy range between 20 to 150 keV. So energy resolution wise, SoLEXS has energy resolution of about 170 eV at 6 keV, whereas CDT has around 1 keV and CZT has around 7 keV. So in the hard X-ray energy range, resolution doesn't really matter because there are not many emission lines present there. So SoLEXS uses two silicon drift detectors, one with the large aperture of about 7 millimeter square and one with the small aperture of about 0.1 millimeter square. So we have built these two different apertures to capture the entire the dynamic range of the sun in the soft X-rays. So large aperture is supposed to be sensitive to the very small A-class or sub-A-class flares, whereas small aperture is supposed to capture very big events like X-class flares without much of a saturation. Right. And CDT has effective geometric area of about 50 millimeter square, and CZT has geometric area of 32 centimeter square. So just to point out, as we are going from soft energies to harder and harder energies, we are increasing our geometric area. This is to compensate basically the power law nature of the solar X-ray spectrum. The big caveat of both of these instruments is these are non-imaging instrument. We just observe sun as a star. So all the X-ray photons that are coming from within the field of view, they are all captured as a single point source, and we don't have any spatial information about them at all. And rest are some of the payload specific specifications. To put our both these SoLEXS and Helios into the broader context, context of solar X-ray spectrometers, which have been flown previously as well. So after World War II, there have been a lot of efforts to observe the X-rays that are coming not only from the sun, but from the different stars as well. And by 1980s, the technology was mature enough that we can analyze these X-rays that are the spectral data that is coming from these X-ray spectrometers and do science out of it. So it was initially most notable missions were Solar Maximum mission, Yoko mission, and Coronal mission. And most of these spectrometers were crystal-based spectrometers, which had a fantastic resolution of about 10 eV, around 6 keV or so, but it had a very narrow observation wavelength band. Right. And by 2000, the technology was advanced enough so that we could use solid state detectors, which were used most notably on SOX, which is again an Indian mission, and of course, famous Resumo mission. So they covered a broader energy range from 2 keV or 4 keV to receive and covered up to gamma rays as well. But resolution for this solid state devices were still kind of around 500 eV or so. For RESI, it was even 1 keV. And by mid 2010s, 2015 or so, the Silicon Drift devices detectors were used by this series of MINX satellite, which was developed in Colorado. And of course, SDD is used in ADITYA-L1 as well. And of course, there are some couple of future missions that are planned in this energy range as well. The biggest caveat of all these older instruments, all the other instruments, is they are mostly mounted on the earthbound low Earth orbits, where your typical orbit time is about 90 minutes, and 30 minutes of it is gone into the Earth eclipse. You cannot really look at the sun because of Earth is in your field of view, and 30 minutes are gone into your South Atlantic anomaly, which is closer to Brazil, right? So in this phase, in South Atlantic anomaly, you have very high particle flux, and this instrument cannot operate in this high particle flux. So effectively, your duty cycle is about only 33% of time. But the huge advantage that Aditya provides is it's orbiting very far away from the Earth, very far away from this eclipsing or SA regions, and it can continuously monitor the sun in all the wavelengths, right? Okay, so where are the soft and hard X-rays that are coming from? So I'm sure all of you have seen this particular cartoon before, but let me just go through it to set the stage for future slides. So to iterate the standard model of solar flares, solar flares are supposed to be started by the magnetic reconnection of the magnetic fields that are there present in the solar corona. So magnetic reconnection basically accelerates the particles, mainly electrons, and these electrons travel downwards along these magnetic field lines. And as they travel downwards, they encounter more denser and colder solar atmosphere called chromosphere, and they heat up the plasma there. And this heated up plasma fills up these magnetic field lines, and these are called evaporations. So all these processes, they produce different signals across most magnetic spectrum. So these non-thermal particles that are impulsive generated during this through the mechanism called non-thermal brainstorming. These non-thermal particles also gyro-rotate around these magnetic field lines and produce microwaves and radio waves as well. And as they encounter and they heat up the plasma there, the heated plasma gets filled up in this loop, and they emit in soft X-rays or extreme ultraviolets by the mechanism of thermal brainstorming. So you see, hard X-rays are very impulsive in nature, and are there for very short duration of time. Whereas soft X-rays, they are more gradual in nature and they decay very gradually, and they are present for longer duration as well. And if you look at the observations that we have captured from our ADITYA-L1 satellite as well, you see exactly this kind of behavior in terms of soft and hard X-rays. So this is one example flare that I've plotted here. On the left hand side, you see a Silicon Drift Detector observations for the soft X-rays. And as you go right towards the rightmost plot, you see a CZT, which observes in the hardest X-ray bands. So you see the most higher energy X-rays are very impulsive, quasi-periodic in nature, and they are very short-lived. And as you go to the lower and lower energies, they become more smoother and more thermal by nature as well. So for example, this blue line presents the lowest energy of 2 to 3 kV, and it's very smooth in nature as well. And if you look at the light curve in longer duration, so this is some 10 days of observation as observed by soft X-rays, and on the y-axis you have flux in the energy range of about 2 to 22 keV. You see there are a lot of flares that are always happening on the sun, and the strength of these flares are variable as well. So in the 10 days only, you see about 3 orders of magnitude of difference in the soft X-rays, and during peak to minima of the solar cycle, we can see about 8 to 9 orders of magnitude of difference. So that's why we went with the dual aperture system for our SoLEXS to capture all these solar maxima as well as solar minima. So here we have also employed our automatic flare detection algorithm, and the peak of the flares are pointed with these different color points. Also, I plotted the long-term background, how the background varies. And if I just plot this across entire duration of our SoLEXS operation, you can see a continuous fluxes that have been started from 2024 January onwards all the way up to current. I think I've plotted till November. Yeah, you see all these big activities in May 2024, in October 2024, and very recently in November and December 2025 as well. So there are about 12,000 flares that we have detected here with our automatic flare detection algorithms, and it gives a very good, nice data set to analyze our solar X-rays in soft X-rays. And of course, we have the similar data set with CDT, and which is in the harder X-rays, and with CZT as well, which is in even harder X-rays up to 150 keV. Okay, so till now, we know that SoLEXS and Helios both are not only photometers, they don't only provide temporal counts, they also provide the spectral information as well. So the spectral information is illustrated in this left-hand side plot. So on the top panel, you have the light curve with counts per second as y-axis. And in the bottom panel, you have y-axis as energy, and the colors represent the intensity at this particular energy. And you see during this very high X-class flares, we have captured all the way from 2 to 22 keV of the solar spectrum. And I've just illustrated some of these different peak of the different classes of flare spectrum here. So you have X class, M class, C class, and B class as well. Right. So what are the different mechanisms that produce the soft X-rays? So we saw in the previous spectrum, there is a continuum as well as there are some emission lines as well. So emission lines are coming from very highly ionized. So we know the temperature of the solar corona is about of the order of megakelvins. And at this temperature, most of the elements are at very highly ionized states. Right. So and these highly ionized elements, they because of the electronic transition between two electron states, they emit these characteristic emission lines. Apart from lines, we have a continuum, which is very well defined by thermal bremsstrahlung. So we have the plasma is highly ionized. So when free electrons interact with the ions, we get the thermal bremsstrahlung if the underlying electron population is thermal in nature. And I've just plotted here how does the spectra in soft X-ray looks like for different temperatures as well. And as you can see, the higher the temperature, the harder it becomes. There are more X-rays at the higher energies as well. And if the underlying population of the electrons is non-thermal in nature, which is possible during the impulsive phase of the solar flare, we see non-thermal bremsstrahlung. So if we assume a power law kind of nature of electron spectrum, we expect to get the power law nature or the broken power law nature in the hard X-rays as well. So in principle, since we have the spectral information from 2 kV to 150 kV, we can fit our spectrum with these thermal and non-thermal models and extract what are the best fit parameters for this temperature, emission measure, and abundances as well. So we employ the particular technique of chi-square minimization to get the best fit models. Also, let me see, yeah. Yeah. Also, we can, since we have temporal evolution of the spectrum, we can do time resolved spectroscopy to get the temporal evolution of different fit parameters, which are temperature, emission measure, and abundances as well. And as you can see here, during decay phase, it comes down back to the normal phase. And since the initial phase, it has barely any structure in it. As it goes into the impulsive phase, there are a lot of emission lines that are present in our spectrum. The spectra becomes harder and harder, indicating the increase in the temperature as well. And as go into the decay phase, the emission line's strength goes down and it becomes softer, indicating the temperature decreasing as well. So if we plot our temperature, which is plotted here in bright blue line, as the flare evolves, and in the background, I have plotted the flux in different energy bands as well. So you can see during the background, the temperature was about, so this is a particular example of M6 class flare, which was happened on 12th February 2024. And you see the background temperature is about 5 megakelvin. And suddenly it rises to about 10 megakelvin in the pre-flare phase. And in the impulsive phase, it suddenly shoots up from 10 megakelvin to about 20 megakelvin. And gradually it decreases back to the normal 5 megakelvin temperatures. So this particular rise from 5 megakelvin to 10 megakelvin is of particular interest to a lot of people. most notably U Hudson, and they call it the hot onset precursor events, where in the absence of any hard X-ray photons, there is arbitrary jump from 5 megakelvin to 10 megakelvin as well. Similarly, we can plot the evolution of emission measure as well. It goes from background values, it gradually increases to the pre-flare levels, and it suddenly shoots up and decays down to some certain value. So this is when the loop are completely filled with the thermal plasma. Also, we can talk about the evolution of abundances as well. So we know the abundances of different elements which has uh, low first ionization potential, for example, iron and calcium. Their coronal abundances are about 3.5 times the photospheric abundances. This is because of Pontomotive force. And during flare, because the lower atmosphere plasma is getting filled up in the loop, we see decrease in these abundances of iron and calcium. They go to the photospheric level. So one defines the photospheric levels. So from coronal levels, they go to the photospheric level and they slowly recovers back to the coronal levels as well. And similarly, the case for the calcium abundance as well. So this is about the thermal part of the spectrum from SoLEXS. Same thing we can do with the non-thermal modeling with the CDT or CZT spectrum as well. So the unique opportunity that ADITYA-L1 provides is we have a continuous spectrum all the way from 2 keV up to 150 keV on the single platform, and with very good resolution. That has never been achieved in history of the solar X-ray observations. So in principle, we can model both the thermal component and non-thermal component, which is traditionally has been very difficult to deconvolve. And yeah, so we can find out what is the thermal and non-thermal evolution of coronal properties during a flare. So this is one, again, a sample example of a simultaneous fitting of soft X-rays and hard X-rays. So as you can see, the fits are still not very good. So this is very much work in progress, and yeah, hopefully it will be completed soon as well. And just to advertise our data products, SoLEXS and Helios, the L1 files, which are spectrogram and light curve files, they are available at this particular website. You can from July 2024 onwards. And we are working on generating the L2 files, which are directly the thermal, temperature, and emission measure parameters directly fitted, and the flare catalog as well given out to you. So we are still working on the L2 data products. Okay. So there are a lot of problems, scientific problems that we are trying to address using the data of SoLEXS and Helios. So in the rest of the talk, let me just concentrate on one of the problems that we have addressed using SoLEXS observations called ion fluorescence in X-class solar flares. Currently, this is in preprint. This is still in revision, so you can access it here. So the idea, so let me again invoke this standard model of solar flares. So we know X-rays are coming from the corona or the upper layers of the solar atmosphere. So most of these X-rays that are produced here, they are mostly emitted outwards towards the deep space, but some of these X-rays that travel downwards towards the photosphere as well. And the upper layers of atmosphere are tenuous enough so that around 5 keV, 10 or 10 keV of photons, they directly travels all the way towards the photosphere without much of the attenuation. And this, we know photosphere, the temperature of photosphere is about 6,000 Kelvin. And so the ion that is present in the photosphere, they exist in the neutral or very weakly ionized form of Fe plus or Fe2 plus. So what can happen? These X-rays that are traveling downwards towards the photosphere, they can interact with this Fe atom, and they can eject the K shell electron here. Once the vacancy in the K shell is created, this vacancy can be filled by either L shell electron or the M shell electron. If it is filled by L shell electron, it produces a character of a photon of very particular wavelength. This is called FeK alpha, and for ion, it has energy of about 6.4 keV. If it is filled by M shell electron, it is called Fe beta, and its energy is about 7.06 kV. So these photons are called X-ray fluorescence. Right. So this is just a cartoon of the X-ray fluorescence. There is this coronal source of the X-ray, which is coming because of the uh, flare, and they can travel downwards towards the photosphere where they can interact with the ion, and in turn they can produce the K alpha, which we can observe here. So these observations have been done in 1980s and 90s using solar maximum mission and Yoko mission. So both these observations done with the bent crystal spectrometers, which had a very good resolution. So you can see a K alpha here. K alpha is actually a doublet, K alpha 1 and of L shell energies. And of course, they have observed the K beta as well. To set it in the broader context, the intensity of Fe alpha is very low as compared to the intensity uh, of this ionized ion. So this comes from the helium-like ion which is present in the solar corona, right? So these are coming from the photosphere, and all these lines are coming from the solar corona, from the helium-like ion. So if you look at the intensity of this particular W line, which is denoted by W, there are orders of magnitude difference. And these observations are taken by bent crystal spectrometers, which has spectral resolution of 10 eV. So the question is, can SDD-based instruments like SoLEXS, which has the resolution of about 170 eV, can still observe these very feeble Fe alpha lines? The answer is quite positive. If we look at the SoLEXS spectrum here, and if we fit, as we have done with the thermal description of our spectrum, we see a very nice residual exactly at 6.4 kV, which is Fe alpha line. And this is a zoomed in view here. So this is one X-class flare which was observed on 1st June 2024. So this says that our thermal description of our spectrum, which is purely from the coronal X-rays point of view, is not sufficient, and there is some extra component which is coming from 6.4 kV. Right. So in 1979, Bay had given what is the theoretical description of this, what should be the flux of this Fe alpha given the geometry of the flare. Right. So he says the flux of K alpha is dependent on the fluorescence efficiency, which in turn is dependent on the temperature of the coronal source that is producing the flare. It also depends upon the photospheric ion abundance, which is denoted by NFE and NH, uh, multi excuse me, multiplied by the geometric factor, where theta is basically the view angle from the observer point of view. So if it is exactly on disk, the view angle is 0, and if it is limb, the view angle is 90 degree. It also depends on the height of the flare, height of the coronal source. So more higher the coronal source, it can expose to the larger solid angle, so that more Fe alpha photons are produced as well. It also depends on the flux of photons that have energy above 7.11 kV. 7.11 kV is the minimum exciting energy that is required to eject the K shell electron from the ion atom, and it depends on the albedo correction factors as well. So for this rest of the presentation, I'll just ignore this particular factor. It has very minimal contribution to the calculation of Fe alpha flux. Okay, just to showcase the dependence in the graphical format. So A depicts the evolution of fluorescence efficiency, this factor here, as a function of temperature. So higher the temperature, the fluorescence efficiency is lower. This is because, as we saw, the higher the temperature, the spectral shape is quite harder. And as we go away from 7.11 kV in energy, the interaction cross sections of photon and the neutral Fe atom becomes lower and lower. Right. So you need kind of temperature about 20 megakelvin or so to effectively produce a large amount of Fe alpha. It also depends linearly or sublinearly about the abundance of Fe. Previously in past, there have been different values suggested for photospheric ion, but the most modern value is about 3.2 into 10 power minus 5 per hydrogen atom. It also depends upon the geometry. So we saw the closer it is to the center on disk, it has higher probability of illuminating the photosphere and these Fe alpha photons directly coming towards the observer. So it has the highest efficiency for viewing angle of 0 degrees, and as we go away from the disk towards the limb, the kind of the photospheric region that is exposed by these coronal X-ray sources become lesser and lesser, and the efficiency reduces. Also, you can see the height of the coronal sources written in this legend as well. And the higher the height of the coronal sources, it has, from geometric point of view, it has more chances of exposing more area of the photosphere. So we have higher efficiency of Fe alpha flux as well, right? So we predict, given this biformalism, that for the limb flares we should not see a lot of Fe alpha flux at all, right? And this is exactly what we observe from our SoLEXS point of view as well. So this is one X class flare that was happened in May 14, 2024. It's a limb flare. It's around X 1.2 class flare, and if we integrate the spectrum at around 10 seconds around this point, and if we plot it and if we fit it with the purely coronal thermal point of view, there is no residual at 6.4 kV at all. Correct. So our entire spectrum has been very well fitted with the only coronal description. And if in contrast, if we go to the disk flare with the theta of about 30 degrees, and it's very similar X 1.2 class flare. And if we fit again, so if we integrate our spectrum for around 10 seconds here, and if we fit with the same thermal component, you see a very nice residual at 6.4 kV here. Correct. So in principle, we can fit this extra component residual with another Gaussian components corresponding to Fe alpha and Fe beta. And also, we have noticed that from our instrument, there is a contamination of nickel as well. So we have fitted with the nickel K alpha and K beta component as well. But if we can focus on the Fe alpha and K beta component, we can fit it and try to calculate what should be the flux, or what is the observed flux from this photospheric ion K alpha, right? So if we do exactly that, if we calculate Fe alpha flux, basically integrating the area under the curve under Gaussian of this fitted line. Also, the major advantage of SoLEXS-like instrument compared to the crystal-based spectrometers is crystal-based spectrometers operated in very narrow wavelength range, so they could observe only the Fe alpha or the different emission lines. But here, along with the Fe alpha flux, we can also monitor what is the exciting flux that we are observing that are coming from the sun as well. So simultaneously, we know from the images what is the position of the particular X class flares that is going on. We can measure the flux of the K alpha. We can measure the flux of electrons, flux of the photons about 7.11 kV, and we can try to match the theory given by Bay. So we have done exactly that. So for the disk flare, if we do that, so this is a bit of involved plot. So on the red, you see a temporal evolution of flux about 7.11 kV, right? And if we, from the fitted Gaussian area under the curve, we have calculated the flux of Fe alpha as well. And this is plotted in this bright blue plot, blue points. And you see both the evolution of flux about 7.11 kV, excuse me, and flux of Fe alpha, the temporal profile match pretty well. And from the base prescription, we can try to calculate, given the heliocentric angle, we can calculate what should be the expected flux of Fe alpha for different heights of 0 arson and 1 arson. And they match pretty well with the observations as well, right? And just for the context, I've just plotted the temperature in black line as well. So it has peak temperature of about 22 megakelvin as well. So if we take the ratio of this Fe alpha flux to the flux of about 7.11 kV, we can calculate what should be the observed fluorescence efficiency. So for this particular flare, the observed fluorescence efficiency is about 0.05. You can see the error bars here as well. And if we do the same analysis for a limb flare, for the same limb flare that we observed, we have the very similar flux above 7.11 kV, but we barely see any K alpha flux here. And if you look at the fluorescence efficiency, basically the ratio of Fe alpha to 7.11 kV flux, it's quite negligible here as well. Okay. And the temperature is quite similar to about 25 megakelvin as well. That should not produce such a less of fluorescence efficiency. So if we do the same procedure for all the X-class flares that are observed in 2024, so 2024 has been notoriously a very active year in terms of solar activity. It has produced around 52 X-class flares, if I remember correctly, and they have it has been very well captured all the solar angles as well. And if you see the month-wise distribution, May alone produced 20 X-class flares, and one particular superactive region that happened in May alone produced some 12 X-class flare as well. So this 12 X-class flare itself, they tracked around 20 degrees all the way to the limb as well. So we can, for a particular active region, we can track how the Fe alpha flux is varying at different heliocentric angles as well, right? So if we do that, and if we plot the fluorescence efficiency during the peak of the flare and plot them against the heliocentric angle, we see a very nice center to limb variation here, right? So for the disk flares, we have comparatively higher fluorescence efficiency, and for the limb flares, we have comparatively lower fluorescence efficiency. Also, all these points are color coded with respect to the peak temperature of the flare. And if you look closely, all these lower points are redder, more redder, which indicates that the hotter the flare is, the fluorescence efficiency is relatively lower, which is exactly as predicted by Bayes' formalism as well. The hotter the coronal exciting coronal source, it should have a lower fluorescence efficiency. So if we further restrict our sample space to the temperatures of only about 20 megakelvin, and if we plot the theoretical curves here for different heights as well, we see a very nice bound for most of the flares. And we can, so for the on-disk flares, we can try to estimate what should be the height of the coronal sources to a certain degree of accuracy as well, which is rather difficult for imaging type of instruments here, right? And for 90 degrees, we have very low fluorescence efficiency. What is more interesting is these 4 points, which are complete outliers. And currently, we don't have any explanation for this particular flares. But what is common about these 4 flares? They are white light flares. And they are mostly coming from superactive regions in the month of May and October. But we don't have any clear hypothesis why this should be very high. Okay. So let me just conclude here. This is all the work we have done till now. So we have looked at the X-ray observations from ADITYA-L1 in in soft X-rays and hard X-rays, from SoLEXS and Helios. We have done Solar's flare spectral analysis in soft X-rays and hard X-rays. How do we fit the soft X-rays and hard X-rays with different models as well? In coming to the conclusion about the ion fluorescence in X-class flares, we have detected from SDD based, we have shown that from the SDD based instruments, it is possible to detect these ion fluorescences. We have also tried to estimate the Fe alpha flux. We have shown the temporal correlation of Fe alpha flux with the exciting flux of about 7.11 kV. We have also shown the heliocentric angle dependence, the central to limb dependence of this fluorescence efficiency. And of course, there are some outliers which are coming from the superactive region. And there is another one particular outlier that we are currently exploring. So excitation by X-rays is only one of the proposed mechanism. There is another proposed mechanism where the non-thermal electrons that are produced during the impulsive phase of the flash, sometimes they can also travel deep towards the photosphere, and these electrons can excite the neutral ion that is present in the photosphere, and they can also produce FEK alpha flux. So in that case, uh, uh, the, the, the flux of FEK alpha should be very co-temporal with the flux of hard X-rays, and that we have observed in one of the flares. So with these observations, let me conclude it here, and I think we have plenty of time for the discussions. Thank you.
Thank you very much, Abhilash. Very nice presentation, very nice research.
Thank you.
You have over this satellite mission. So from now, I will open any questions from the public, please. El Paulo, you ready?
Thank you. Abhilash, thank you for the talk. Congratulations to all the team for all the spacecraft flying. We realized the challenges in all sorts of points of view, let's say, and getting all these nice results, keeping the soft and hard X-ray spectroscopy alive, because of course after RESI we've been struggling, right, to get the short-lived missions here and there, but it's good to have a long-term view on that coverage of the spectrum there. And lastly, quite interesting results on this K alpha shell. That's yeah, I wasn't aware of all that, so I'm learning. So I have a couple of questions. Might intersect with other questions here, but I think the first is regarding the first part of your talk about the instruments themselves. On the data analysis of the soft and hard X-rays, right? So a couple of quick questions just to clarify my view.
Sure.
For this soft X-rays is SDD2, right? Is the yeah. So you mentioned I think there are 3 channels.
There are 2 channels. Okay, let me go.
There are 2 channels. Yeah, 2 to 3. So
yeah,
they got confused there. 2 channels. They're not.
Yeah, so there are 2 channels for SoLEXS and 2 separate detectors for Helios, CDT and CZT.
Yeah. No, I'm thinking how it might be interesting to check how that compares. You probably did this with GOES filters, right? Because GOES they have the weird broadband filters. They overlap. It's a mess. I'm wondering how if you did have time to check and compare in terms of the responses and fluxes, because all the I'm thinking that in 2 terms. Well, of course, the instrumental part of the things as well, but in terms of the temperature emission measure values that we get from usually right from the decades of GOES, now with these, how they match or don't, right? In particular to the hot onset aspects. I'm also very, very interested in that aspect, working with you on that first paper and continuing on the side of other things. So on that first, I don't know if you have any
So
work on that. So please,
So of course we have 2 channels, one with the larger aperture and one with the smaller aperture. So currently we are being in the solar maxima. Sadly, our larger aperture is kind of saturated. We don't have very good science quality data with this, and we are still struggling with the calibrating it. For the smaller aperture, which we call it as SDD2, it is very well cross-calibrated with GOES. So the problem is it starts with the energy range 2 to 22 kV, and the 2 GOES bands are, in terms of energy, they are 1.2 to 12 kV. One is 1.2 to 12 kV, and another one is about 3 to 24 kV. So we could only cross-calibrate with the 3 to 24 kV aspect, and it has been very well cross-calibrated. The fluxes are quite one-to-one.
Quite
And
similar.
the results, Yeah, the results are even published. You can check out the
Okay.
calibration of SoLEXS. Yeah.
Oh, pretty cool.
We have also done the kind of peak temperature comparison from GOES as well as SoLEXS as well. And we also have I think this was done for RESI as well, if I remember correctly.
Yep, yep.
And we also see a kind of underestimation of GOES temperatures by about, so we have even more underestimation as compared to RESI's estimation. So it's about 70%. And it really depends if you calculate the GOES temperatures, assuming coronal abundances or photospheric abundances.
Yeah,
So
yeah. So it's
people,
similar
I think,
to
usually use
RESI.
coronal
Yeah,
abundances.
yeah.
So we see a tighter correlation between GOES and SoLEXS if we use photospheric abundances, particularly at the peak of the flare.
Yeah. No, that's quite interesting. That especially that matches that discrepancy from the RESI
Correct.
results back in the day.
It does.
Quick one now that you opened for other people. Software for data analysis. Is
Yes.
that available? How can we learn how to
Yes.
play? Is
Yes. Okay.
IDL based? Is Python based?
Yes, good question. I think I should have included a lot more details here, but I did not. Okay, so let me quickly go to this slide. Okay, so data and the software is also available on this particular website, which is handled by ISRO. And currently, there are some calibrations that are missing from the software. For example, dead time correction, which is important for getting the absolute fluxes, which are comparable
Mhm.
to GOES. That is currently missing, but we are working on
Yeah.
it. And so there is January next year, 2026. There is a ISRO ISA workshop where the uh, the Solar Orbiter team and the ADITYA-L1 team, they have a joint collaboration. So personally, my aim is to release the perfect software before that January 2026.
Cool.
So by that time, I'll notify you once again. All the dead time correction routines should be up there as well. And for the fitting point of view, we are moving towards SunKit specs, if you are aware, which is a Python-based
Yep.
models, which
Yep.
have been migrated from OSPEX to SunKit specs. Right. And but for fitting, I'm using share pass fitting. From experience, SunKit specs fitting routines are not robust enough, and we have to invoke some other. You can either use XSpec or Sherpa. So I'm going with Sherpa. So all these codes, I think Soumya also worked on exactly
Yep.
this,
Yep.
and she has some of the codes as well. And all these codes, I'll make a notebook, and by 1 month time scale, I'll make it public. So that's the
Oh,
plan.
that's awesome. Yeah, I'm a dinosaur going from back from IDL and all specs. But yeah, of course, yeah, there's the newer generation of working on all the
Correct.
Python
Yeah.
based
Yeah.
stuff. Cool.
Yes.
Thank you so much, Abhilash.
Yeah.
Yeah, I'll
Thank you.
open the floor for other questions.
Yeah. So if you have any questions, just write to me. I've skipped a lot of details from this. If you have particular
Yeah,
questions, you can just shoot me a mail.
cool. Thank you.
Okay, any other questions?
Don't be shy, people. Ask your questions.
So I just want to, since there are no more questions, I just want to get your view on this particular. Let me just, okay. Is my screen still visible?
Top area.
Okay, let me share my screen once again. Just hold on. I just wanted to show some backup slide and get your views on it, but I can't seem to do that.
That's always good. After that, I have one more question.
Yeah, sure. I hope you can see my screen again.
Yes.
Yes. So this is the particular flare that I was talking about. And of course, I mean, this is clearly work in progress. And in blue, you have this FEK alpha flux, and you have this exciting 7.11 kV. And in these two colors, you have conus wind data in the energy range of 2 to 80 kV and 80 to 300 kV. So if you see this particular region of interest, it clearly tracks the hard X-rays. And we are
Yeah.
theorizing that this is because of the electron impact ionization rather than the photon ionization.
Yeah. Yeah. Which is probably similar, at least according to Radin simulations. You get a quicker and stronger ionization in the chromosphere by just non-thermal electrons falling into the chromosphere than just the heating.
Correct.
According to simulations, right? As you
Yeah.
mentioned there in one slide, some models are wrong. Some are useful.
Correct.
Yeah.
Yeah.
That's pretty interesting. And
Yes.
my question would be actually similar to that, because that answers partly my question is in terms of the K-shell or even the spectral lines, right, the high temperature lines, if you had time to check in terms of the hot onsets, if they pop up. I know you showed the time evolution, right? They start to pop up later on, but maybe there's, I don't know if you had time to check that let's say, check the initial high temperature in terms of the line intensities, not just the thermal fitting, the Ramsau stuff.
Yeah. Yeah.
That might be, I
Yeah.
don't
That
know.
is tough to do because we don't have a lot of signal there, and this particular
Yep, that's why I'm
fitting line is
asking.
very, very difficult. Yeah.
No,
So that's why
yeah,
we chose the peak of the X-class flare rather
yeah,
than some
that's
smaller
easier
class
to
flares.
see.
So we'll probably develop some novel techniques to really extract this flux and just
Yeah,
do for our entire data set, just try to extract this FEK alpha flux.
that's pretty cool. Yeah,
Yeah.
and it's part of that question. Newport effects, right? Because you have all the tools.
Right.
So the soft and hard X-rays at the same time from the kind of same-ish instruments. Don't know if you had time to
Yeah.
check on that stuff. I'm
Yeah.
asking this because both Somi and Solomon just had a paper pretty much kind of accepted. So they got the last review, which is very positive in terms of the Newport effect analysis. So we're kind of thinking that ballpark again. So I'm
Yes.
curious.
So that is very much doable, and one of my colleagues is already doing that. He's looking from a QPP point of view as well as Newport effect point of view, and there is very good evidence that almost 80% of the flares follow this Newport effect as well. So yeah, they have the fantastic
Awesome.
results as well. And I
Yeah.
don't have much of details on that, but I think that will be published soon as well.
Oh, that's nice. That's nice to hear.
Yes.
I'll keep my eyes open for that.
Yes, definitely. Yeah.
Abhilash, I saw that you show a lot of flares from May 2024.
Yes.
I believe most of them are from the famous May
Same active region. Yeah.
Mother Day storms, right?
Correct, exactly. Yes.
Okay.
Yeah,
So,
that week, I think 8 to 14.
correct.
Yeah,
Yeah.
from 9.
Yeah.
And there's
And
also one in October, I think that.
correct. So
Yeah.
if you look at these 4 points here, 3 of them, okay, 2 of them are from the active region 3664. I think these
Yeah.
2. One of them is just before that particular active region, 13633 or 13663. And this is the October, not the 1st October. This is the 9th October flare.
Okay.
I forgot its active region number. But yeah, all of these are super active regions. We have no idea why this should be. No conjecture at all. This
So
is
probably
just
for like super flare sends a higher level of X-ray.
no.
Maybe.
If it is X-ray, then we should have captured it as well. So it should be
Okay.
a very directed towards the photosphere X-rays, which we are not able to capture. that seems quite unlikely.
Okay.
Unless it is hard X-rays, it should not be directed. It should be isotopic. So very puzzling. So what we are thinking is probably more ion present there. Neutral ion cannot be present in such high quantity, but Fe plus and Fe2 plus being present in somewhat higher quantity is what we are thinking, but no idea.
Mhm.
And most of them being the white light flare also gives you some kind of idea. But there are cases where it is a white light flare, but we see a normal fluorescence efficiency. So that also doesn't fit really into the picture. So yeah, we are still working on this.
Okay. Any other questions?
No, for me, I'm happy. Thank you so much, Abhilash.
Thank you.
So thank you for the presentation, and also thank you, Paulo and Solomon, to invite you, and Fabian, if you have any words too.
Oh no, just to thank Abhilash again for
Thank you.
accepting our
Thank you for
invitation.
inviting me.
Very nice talk. Thank you.
Thank you. It was
Yeah,
a pleasure to speak here.
Yeah, let's
right.
keep in touch, Abhilash, because
Yes, definitely. Yeah.
there's some converging interests there as we discussed. It's
So,
been
I
a
mean,
while
just to
since.
update some of the work also we are doing, since I forgot to talk about hope phase as well. So we are kind of exploring this hope phase as well, but we don't have really, rather than success, we don't have how to approach it, how to, because we have huge data set. I don't know how to converge the hope and non-hope phase.
Send me an email.
Yeah, definitely.
I'm not directly working on this, but I have a colleague that's exploring that in terms of in a statistical approach.
Okay.
In thinking of, we're discussing how to establish some more systematic ways
Okay.
to define what it is and how to detect. And this is with Douglas postdoc with me a couple year ago. Yeah, about that. 2 years ago. He did by hand, right? It was a 2-year period of data, just selecting ranges one by one, flare by flare, because it's hard to get a clear.
It is very hard.
Yeah, how to automatically they say, oh, this is the beginning of a flare or the hope period or something.
Okay.
But we have ideas and be happy to discuss.
Yes,
For sure.
let's set up a meeting if you're free, probably
Yeah.
after Christmas break.
Yes, for sure. For sure.
I'll write to you, definitely.
Awesome.
Yes, thank you.
Thank you. Bye, everyone.
Thank you. Thank you for
Right.
the meeting.
Bye-bye.
Thank you.
Bye.
Bye, Abhilash. See you soon.
See you. Yeah,
Bye bye, everyone.
bye.